Hello and welcome to the second half of the introduction to the Analogue labs in week 5. This time looking at summing amplifiers, how to simulate amplifiers, and the summing amplifiers on the VAM, how to design and build them. Firstly, note that for inverting amplifiers with more than one input, by which I mean an inverting summing amplifier, we have this formula for the 3 dB bandwidth. It's the grain bandwidth product of the op-amp, which hopefully you should already have measured from the non-inverting op-amp, divided by 1 plus the sum of the modulus of all of the gains. The derivation of that result is a little bit messy. Do have a look at the short introduction to op-amp amplifier bandwidths if you're interested in the details. You can simulate bandwidths on the simulator. It will plot a Bode type plot for you when you're in AC mode if you put it into frequency response mode. For example, here I've selected a summing amplifier with 3 inputs. This is the preset Lab 08 summing from the AEP Spring Terms preset group. Not autumn term labs, spring term labs. Summing, that one. Now this summing amplifier has, at the moment, 2 inputs. This one here, 1 volt, going through that 1K resistor, and another input here, which at the moment just has 0 volts or connected to ground on it. And those two are going through this op-amp here with a gain bandwidth product of 3 megahertz. So, you would expect the 3 dB bandwidth of this to be 3 divided by 1 plus the sum of the modulus of the gains. This input has a gain of -1 to the output. This input also has a gain of -1 through to the output. So that would be 3 megahertz divided by 1 plus 1 plus 1, which is 3 megahertz divided by 1 plus 1 plus 1, or 3 megahertz divided by 3, or just 1 megahertz. So we're expecting the bandwidth of this op-amp amplifier to be 1 megahertz. Is it? Well, here, at low frequencies, we're getting a gain of approximately 0 dBs. If I go up to 1 megahertz, I would expect the gain to be 3 dBs below that, and yes, pretty much that's exactly where it is. Remember, 3 dB down is a factor of 1 over the square root of 2 in amplitude, and indeed the amplitude has dropped by 1 over the square root of 2 to a value of 0.707 volts, 707 millivolts. So that is working exactly as we would expect. We are 3 dBs down at 1 megahertz, which is the predicted bandwidth of this amplifier. Now, when we talk about bandwidths, we usually mean the 3 dB bandwidth. But quite often, we're interested in other bandwidths as well. A 1 dB bandwidth or a 10 dB bandwidth or anywhere in between. And there's a formula in the lectures for deriving what the X dB bandwidth is in terms of the 3 dB bandwidth. And this is a table constructed from that formula. It will be useful to have this on hand, or at least make a note of some of the key results. The key result, I think most important here, is the 0.2 dB result. The 0.2 dB bandwidth is 0.217 times the 3 dB bandwidth. Because we are going to be looking at the design of the summing amplifiers on the VAM. Now, the first requirement for this amplifier is that the input impedance has got to be within 2% of 100K at 1 kilohertz. And the second is that the gain has to be within 0.2 dBs of 0 dBs from 40 kilohertz to 20 kilohertz. How do you design this? In other words, how do you pick the values of C, R1 and R2 in order to get both of these specifications achieved? Well, first of all, the input impedance. For a summing amplifier like this node is known as a virtual earth point. It's held at ground all the time. It is at 0 volts, but it's not a real ground point because current cannot flow directly from it to ground. We know it's at 0 volts because the op-amp is not saturating, and an op-amp which is not saturating is trying to get its two inputs to be at the same voltage. Its non-inverting input is tied to 0 volts directly, so the op-amp will be trying to keep its inverting input at 0 volts as well. Now that means that looking into this circuit, what any signal or system trying to drive into this circuit would see is a series combination of this capacitor and this resistor driving into ground. You can think of it like this. We have a signal input which goes through a C and an R to what is in effect ground. The input impedance is Vin divided by In, the current that's coming in from the input here. So that's my input impedance, Vin over In. Well, if I apply Ohm's law to this circuit here, Vin is the voltage across this network, In is the current through this network, so the impedance of this network by Ohm's law will just be Vin over In. In other words, that is Rin. The input impedance is the impedance of the capacitor in series with the impedance of the resistor, which, as we know, is 1 over j omega c plus R, in this case R1. That we need to be within 2% of 100k at 1 kilohertz. Right. The thing to realize here is that if this circuit is going to have a reasonably frequency-independent behavior over most of the audio frequencies, which we want it to do, then this term here, due to the capacitor, will be negligible compared to the term R1 due to the resistor. It's certainly going to be negligible at high frequencies where this term here is much smaller. It's only going to become a problem, perhaps, at very low frequencies where this first term here is at its largest. Remember, it's proportional to 1 over the frequency, so as the frequency goes down, this term here gets bigger. It's going to have a big effect at low frequencies, but not at high frequencies. Over most of the audio range, we're just going to have the input impedance being approximately equal to R1, and therefore, to get R1 to the 100 kilo ohms we require, R1 would be most sensibly picked to be 100k. We also want the gain to be within 0.2 dB over a wide frequency range, and for most of the frequency range, as noted, this term from the capacitance is not going to have a significant effect. So that means that for most of the frequency range, we've got a op-amp inverting amplifier, which just looks like this. We know this is 100k. We know that we want the output to be approximately the same magnitude as the input, because the gain, 0 dB, is telling us that the output amplitude should be approximately the same as the input amplitude. And the only way we can do that is to have this resistor the same value as this resistor. So that sets those two resistors. Then we have the hard one. We have the case that we need to spend a bit more time on, which is how do you satisfy the requirement of 0.2 dB down at the lowest frequencies, at 40 Hertz, when the capacitance is going to have the biggest value. Right, well, the gain of a inverting amplifier like this is the feedback resistor, in this case 100K, divided by the input resistor, which in this case is 1 over j omega c plus R1, which is also 100K. I shouldn't have said input resistor there. The input impedance, the impedance of this network here. The gain is actually minus that because it's an inverting amplifier, but since we're just looking at the amplitudes here, we just want the modulus of the gain. It doesn't really matter whether I write that minus value or not. The magnitude of this isn't going to change. And I want that gain at 40 Hertz to be no less than 10 to the power of minus 0.2 over 20, because that would be 0.2 dBs down on 0 dBs. In other words, at 40 Hertz, I need 100K over the magnitude of 1 over j omega c plus 100K to be greater than or equal to 10 to the power of minus 0.2 over 20. And then it's just doing some algebra on that. I think I might leave that as an exercise for you. Oh, I've obviously given you a few hints here. 10 to the power of minus 0.2 over 20 works out to be about 0.997. So that gets you down to this expression here. And this is the modulus here. And if you remember how to work out moduli, the easiest way to do that is to think of that point there in terms of its real and imaginary parts and apply Pythagoras. So we've got this point here would have a real part of 100K and an imaginary part of minus 1 over omega c. It would be round about there, where this is 100K and the length from here to here is 1 over omega c. The magnitude of that is then the hypotenuse of this right-angled triangle. Oops, you can't see that, sorry. Yeah, just about. Going through some algebra, work out a result like this, stick in your value for R1, and you should get out a value of C, which is a minimum value of C. You can then pick any value you like of C bigger than that value, provided it fits into the holes in the VAM board. And there's a little bit in the lab script about how to fit different sizes of capacitor into the VAM board. So again, do read the how to build the VAM before actually trying to do any build. And also, if you're running out of time, some of the summing amplifier experiments can be done outside the lab hours, just in the simulator. The most important thing to do is to get those calculations done and to get the VAM circuit built in the labs themselves. This is just a repeat of what I said yesterday about measuring small signals on the scope. And yep, I think that's all I need to say this time. Good luck, and I hope to see you in the labs.